This is a video for P3. I'm just going over a few of the questions from the chapter review 6, differentiation, for the EdExcel P3 syllabus. So a lot of students ask me for sort of a summary. What I'm doing is I'm using the solution bank. So if you don't already know about solution bank, head over to solution bank and see the worked examples, as that's a very good resource to make use of. But sometimes my students, even with the solution bank, struggle to get through to, what did I do? The full answer. So I'm just going to go through a couple and see what happens. So, okay, so let's look at these first two here. So number 1A just asks to differentiate each time. So a lin, anything with a lin in, what happens when you differentiate, or how do you differentiate anything with lin, natural logs? Well, the first thing I would do with this is just to notice that this 2 by log laws can just go over here. Okay, so this is equal to this. And the second thing that I would notice is the rule: if you have a y equal to ln x, then your dy dx, your first derivative, is 1 over x. Okay, so we can use this rule, and when you apply this rule, the a value stays the same. So our a value is this 2. So if we had, for example, a ln x, then it would be a over x. Okay, so obviously, maybe we can already see the answer is going to be dy dx. Dy dx, it will end up being 2 times 1 over x, which is going to just be 2 over x. So just take a look at that a value, where it goes. So that's the first one. The second one, b, x squared sine of 3x. Okay. So here we have this function, which is, some sort of x, it's like a polynomial function, and times by a sine function. Okay. So obviously, as soon as I see a function times a function, at least especially in P3, I think the product rule, because we're timesing 2 functions. So the product rule u dash v plus v dash u, where u is one of the functions and v is the other function. So we could call this one u and this one v. And obviously u dash is the first derivative of u and v dash is the first derivative of v. Okay, so if we set up our u and our v, sine 3x, first derivative of x squared is just 2x. First derivative of sine x, so if that 3 wasn't there, first derivative of sine x is cos x. So if I were to draw that out, so if we had sine x then as our function, then dy dx is going to be cos x. Now, this I need to, at the end of this video, maybe find a good way to remember it, but as we go, maybe I'll remember which one. Sometimes it's negative, so I think if you go from cos to sine, it's negative, but I'll just have to recheck that at the end of the video. So this would be the usual baby one, but we have one with an a value of 3. So that because it's got this, and when I say a value, I just mean it's like it's got some sort of constant. So it has a function inside a function. So we're actually dealing with our y is sine some sort of constant at times of x. So this is a function inside a function. And then what you do is a kind of like a version of the chain rule. So you have to, if y equals sine ax, make myself some space here, then our dy dx will be that a times by sine ax. So everything stays the same, but we have to times it by the first derivative of the baby function, the function inside the function. So this function, if this function was our y, run out of colors, then dy dx equals a. So that's what this is here. Okay. So when we're deriving, we times it by the first derivative of what's inside the function. Which, so if we go back to our v dash, we end up with sine 3x times by the first derivative of 3x, which is 3. So 3 sine 3x. If you were to write that sort of, oh, not like that. Let's just do this. There we go. Okay, 3 sine 3x. Where were we? So now we've got our u and our v and our u dash and our v dash. And the next step is we want to do our little arrows. So we do 2x, u dash times v is our first section. U dash is 2x times 2x times sine 3x. And we're adding it to v dash times u, v dash times u, v dash times u. So that's going to be 3 sine 3x times by x squared. Okay. So I'm just setting this up as like in the order that I would teach it. Of course, as you get good at these things, you'd maybe be able to put it in order straight away. See, I made an error here. So, whoopsie daisies, sine goes to cos. Let's just fix that first. Okay. So if I were to follow the mark scheme on the solution bank, this is cos 3x, and this was dy dx. I just switch it around to make sure it just looks the same. So the 3 cos 3x x squared becomes 3x squared cos 3x and 2x sine 3x. Okay. And that's completed. So that's number B. Question 2. Question 2a, we're looking at this question to given that 2y is equal to x minus sine x cos x, then they've x is between 0 and 2 pi, so 0, 360. So the question is, we have to show that dy dx is equal to sine squared x. Okay, so first of all, we want to divide by 2. So we want, obviously, we want y on its own so that this is not standard form. So divide the whole thing by 2. That's a funny divide sign. Divide by 2. And we end up with y equals a half x minus a half sine x cos x. Okay. So we are aiming to make it look, always just think about what you're aiming to make it look like. Well, from here, this half x, I think we can manage with, but let's take a look at the couple of ways to do this. Just looking at the solution bank, it can approach this as a product rule. So let's look at it that way. So if we approach this right-hand side, this part, as a product rule, we're gonna, if we did dy dx of a half x, so just that's just going to be a half. So dy dx of a half x is just going to be a half. But now we're looking at this green part here. So we make a product rule again. Product rule is u dash v plus v dash u. Let's let our u be a half sine x. And let our v be cos x. Okay, so this, I think my previous question I had, this will sort it out nicely, which goes which. So let's take a look. U dash sine goes to cos. So this will just be, the a value stays the same, the a value being the constant involved there. So it's cos x, let me get that right. And v dash is negative, so cos goes to negative sine x. Okay, so just to answer my own question from the previous example, cos goes to negative sine, sine goes to cos. Okay. Then we need u dash v plus v dash u. So u dash v that way, v dash u that way. Don't forget there was a negative there. So u dash times v is a half cos x, well, squared. And then we have negative a half sine squared x. Okay. So that's just timesing u dash v, v dash u. Okay. It's something we can work with. So, oopsie. Misbehaving Zoom function. dy dx, if we simplify this a little bit, it's going to be a half plus a half sine squared x. So it just went to the second one first, minus a half cos squared x. Okay. Now we take out a half as a common factor. So a half plus a half sine squared x. So like kind of see what I'm doing there is I'm setting it up to kind of get the sine and cos on its own somehow. So just to, let me just check that did I do this correctly? Negative times a negative is a positive, positive times a negative is a negative. Okay, minus cos, whoopsie. I was hoping for a plus in the middle there, but we still have something we can work with. Let's just holding this thought at the end. I want to try and use this. So just bearing in mind that we want to end with sine squared x. So we're trying to manipulate this to look like sine squared x. So far it doesn't look like sine squared x. I wanted all sines. So if we wanted cos squared x to look like sine squared x, then we would say sine squared x, if I just manipulate this, is equal to 1 minus cos squared x. This is one of your identities, of course. So if I just sub this in somewhere, so wherever you see a Oh, this would make it all causes. I don't feel like go in a different direction. We want to make it all sine. Let's try the other way. So sine squared x equals, whoopsie. Negative cos squared x equals 1 minus. I see what's wrong with this. This identity is a plus. There we go. Okay. So cos squared x is equal to 1 minus sine squared x. Okay, so I am just detouring slightly off the mark scheme here. I'm going to switch this for the cos squared x over there and just see what happens. We get a half plus a half sine squared x minus 1 minus sine squared x. So I just switched those up. Reason I chose this way is just I want to get sine squared x on its own in the answer. Let's simplify some more. So half sine squared x minus 1 plus sine squared x. Oh, what's going on there? Let's keep going. A half plus a half 2 sine squared x minus 1. Whoa, what's this? A half. Let's times that in. So that's just sine squared x because it's a half times 2 minus 1 times a half is a half. Look at this. Done. Okay. Which equals sine squared x. Went a bit rogue of the mark scheme, but we got there in the end. All right. That was number A. B just is a little bit of application of sort of pure math stuff. So it wants us to find the coordinates of the point of inflection of this curve. So usually these questions follow on. So we know that dy dx was sine squared x. So this is where we start. That was proven already. Other information that you need in order to answer this question is a point of inflection. At any points of inflection, your second derivative is equal to 0. Okay. So this is the first derivative dy dx. So let's look at the second derivative. How do we get the second derivative? Well, we have sine x squared. If that's just another way of writing it. So we can chain rule this thing. Quickly looking at the chain rule. So if we were to write the chain rule, if y is equal to some sort of function to the power of something, then we minus 1. We're going the other way around. So we times by n. dy dx is we times by n. And then we place the whole function. And then we minus 1 from the n. And then we times it by the first derivative of whatever's inside the brackets. Okay. First derivative of whatever's inside the brackets. So we chain rule that. So if we apply this to our sine squared x, we have our n is 2. So our dy dx of dy dx. So let's call it d squared y over dx squared. This is just the correct notation for second derivative. So n goes down 2. Just keep everything inside the brackets, sine x. And then we have to times it by the first derivative of sine x, which is just cos x, and it stays positive. Okay. 2 sine x cos x. 2 sine x cos x we know is a identity that will just be, sorry, not an identity. It's a double angle formula. it just becomes sine 2x. Okay. Have we answered the question? Not at all. Let's take a look. Find the coordinates of the points of inflection. So we said that the point of inflection, the second derivative must be equal to 0. So we can put this equal to 0. I'm going to make some space. So where are we? We have sine 2x equal to 0, and we want the points of inflection, and there will be 2 of them. So how do we solve this? Well, don't forget, there's many different methods to solve this. I'm going to pick a kind of visual method, but first let's just get, so I like to get 2x on its own. So 2x on its own, we take sine to the minus 1. That would solve that. Sine to the minus 1 is 0. So if I were to draw this, we're looking at a sine graph where x is 0. So now just keep this 2x there until the end, okay? Because that would squish your graph or stretch your graph. So for now, let's just look at a normal sine graph. So if we had sine x, for example, go up, down like this, and just keep going forever. But we know we're only going, that the restriction was only to 2 pi. So 2 pi is over here, 2 pi. Okay. So this middle part is just pi, and this is 0. So we're looking at, basically, this is saying, where is y 0? Okay, y is 0. So somewhere on this line, y is 0 over here. So anything on this line. But this is our sine x graph. We're not using sine x, we're using sine 2x. So visually, we could do this. Sine 2x. So it's all the points have been squished up. So this stays 0. This is pi over 2. And this is 2 pi over 2, which is just pi. So, and that just keeps going. And now we obviously have more points because we want to go all the way to pi. So if I continue this growing, we want to go all the way to pi. Okay. The next one would be, this would have been 3 pi over 2, and this would be 4 pi over 2, which is obviously 2 pi. So just to see sort of how that looks, these are all our points where y, well, what is on the y-axis is equal to 0. Okay, this is our x-axis, which is now in terms of pi. Or in degrees. It's not really, this is just how I teach it. So this is just, we're working with radian. It's our radians axis. Okay. So how does this help us? Well, we could do this visually. Visually, we have a few points so that we've already got on the graph. So we have pi over 2 as an option. We have, that's pi over 2. We have pi. We have 3 pi over 2. And we have pi. Okay. This is, so we did this visually. What did I do here? Pi over 2. Pi. Oh, oopsie. This one's 2 pi. Okay, I just checking my restriction again. It was not including. So just to take a look at this restriction, always check your restrictions at the end. This here, not including. So it's not including 2 pi. And that should be it. If we had taken it from this 2x point, we would have had to use this graph, and then at the end you divide by 2. But I decided to just sort of do it visually as I was going. Checking the mark scheme, we have pi over 2, pi, and 3 pi over 2. Okay, that's all our options. Good. Okay, so we're not finish, we've got the x's of our points of inflection. So we want to first just get the y's and check them. So let's see, the way to get the y is to just sub it back in. If we had our f of x, for example, was, what was our f of x from the previous question? I just grab it for you. X over 2 minus a half sine x cos x. So just sub in everywhere you see an x. So for this one, our y would be f of pi over 2. And using this formula, that would be pi over 2 minus a half sine pi over 2 cos pi over 2. And do this for all three. So this one would be f of pi, and this one would be f of 3 pi over 2. Okay, so we're just subbing it in. Use your calculator, and I get, for this first one, I get pi over 4. The next one, when it's pi, I get pi over 2. And the last one, I get 3 pi over 4. Okay. So what I have proved so far is our possible points of inflection. Our possible points of inflection are, let's take a look. So we have this and this. Oopsie, no, not that. Here. We have this, and we have this and this. So our possible answers is x over 2. That's not an x. That's a pi over 2, pi over 4. Another one is pi over 2. And another one is 3 pi over 2, 3 pi over 4. Okay. So those should all be correct, but I'm just looking at the mark scheme here. They want you to check it. So let's see. In order to check each of those is valid, so to check these are valid, you want to make sure there's a sign change. So it's either going from positive to negative or from negative to positive on either side of this x. Okay. And that will make it a point of inflection. So it's going to either go from positive to negative or negative to positive on either side of these. Ooh, that's not how a negative sign goes. So I'm just going to follow the mark scheme. They picked for pi over 2, they picked pi over 3. So pi over 3, being bigger. So pi over 3 is bigger than pi over 2. So that's on one side. And then they checked that. And when they sub that into the second derivative, so you find f dash dash of this. Okay. So you sub that into the second derivative. So let me just quickly grab that for you. We had second derivative was, where is it? No. A lot going on here. First derivative was sine 2x. Where's my second derivative? There it is. 2 sine x cos x. Okay, so it's sine 2x. So basically on your calculator, you just go sine 2 pi over 3, and you see what that comes up with. So the answer is 0.36 something, but the only thing that you need to be concerned with is that it's positive. Okay, that's positive. So now we want to choose something that's And this was bigger. This was bigger than pi over 2. So this is on the one side of it. So if we had pi over 2 in the middle, this is pi over 2. Whoopsie. Then pi over 3 is on this side. Okay. Then they've picked, for the other side, they picked 3 pi over 4. So you sub that in here. You sub that into sine 2x. So you put 3 pi over 4 here in your calculator. I had my calculator in degree mode, so that didn't work. But if you put it into radian modes, you should get -1, which is negative. So the second derivative is negative here, positive here. Therefore, it's a point of inflection. Okay, the sign has to change or it's not a point of inflection. Let's try the next one. So just make space here. We have to make sure there's a sign change. So the first one is valid. First one is valid. There was a sign change. Doing the second one. So we want to find the second derivative of pi. You have to find something bigger and something smaller. So if we have pi, you've got to put something above it and something below it. They've used 3 pi over 4 and 5 pi over 4. So we have 3 pi over 4. I'm just going to write this in radians so that 2.356. And then we have 5 pi over 4. Easier to see what we're working with. 5 pi over 4 is 3.92. These are radians. And of course, we just have pi. If you put that in radians as well, it's going to be 3.14. So just to see which one's big. I mean, some of my students can do this, others can't. I like to convert it. So see. So we need to see a sign change from this to this. We want to see one of them must be positive or negative. They have to be different to each other. So if we sub this in, we first sub in 3 pi, put this in your calculator. So that's going to be sine 3 pi over 4. Sine 3 pi over 4, sine 2 3 pi is -1. And if we put 5 pi over 4, it's 1. So this one's negative, this one's positive, and there's a sign change. Okay, do the same for the third one. They've done it in the answer sheets, and there was a sign change again. So these are all valid points of inflection. Good. I think that completes number 2.